In this video, we will continue our practice with z-scores. If we know the mean and the standard deviation for a set of data that forms a normal curve or a bell curve, then we can convert the data from whatever it is into this z-score so we can easily compare, even if we're talking about two very different data sets. The formula for z-score is that the z-score value is the original value minus the mean divided by the standard deviation. Jack and Jill. Jill scored a 710 on the verbal part of the SAT. SAT verbal scores have a mean of 500 and a standard deviation of 100. Her boyfriend Jack took the American College testing, test, and scored 27 on the verbal part. ACT scores are normally distributed with a mean of 18 and a standard deviation of 6. Assuming the two tests measure the same ability, who did better? So without z-scores, it would be kind of tough to know. There are two different tests, 710, 27. How do you compare? But that's where z-scores come in. So let's look at Jill's z-score. So I'll call it z, and I'll put a little j on it for Jill. Jill's z-score is going to be her original value here of 710 minus the mean, which is 500, divided by the standard deviation, which is 100. Alright, so Jill's z-score is going to be 700 minus 500 is 200. So we're looking at 210 divided by 100. Of course, dividing by 100 means moving the decimal point twice to the left. So we're looking at a z-score of 2.1. Alright, that means that Jill scored two standard deviations, a little bit more than two standard deviations above the mean. That's a pretty great score. In fact, let's find Jill on a normal curve. Alright, the mean is right here in the middle. Actually, we know what the mean is, don't we? The mean is 500. Okay, so in this case of the SATs, 500 is right here in the middle. Now, Jill scored a little more than two standard deviations above that. So this line is one standard deviation, two standard deviations. So here's Jill right here. Alright, in terms of the normal curve. Now let's compare that with Jack. So for Jack, okay, I guess that J doesn't really help because they're both J's. I didn't think that through. So here comes Jack. Jack's z-score, he got a 27, alright, but the mean was 18 and the standard deviation was 6. Alright, so Jack's z-score is 27 minus 18 divided by 6. Alright, of course 27 divided by 18 is 9, so we're talking about 9 divided by 6, which is equal to 1.5. Okay, so that means Jack scored 1.5 standard deviations above the mean. So let's look back at our normal curve. Alright, here's one standard deviation. So Jack scored 1.5 standard deviations above the mean. I'll show Jack here in blue. So here's Jack. Okay, Jack's here at 1.5 standard deviations, and Jill's here at 2.1 standard deviations above the mean. So Jack outperformed Jill by a pretty significant amount. So specifically, you could say Jill did better than Jack since she scored 2.1 standard deviations above the mean, while Jack only scored 1.5 standard deviations above the mean. Number 2, books in the library are found to have average length of 300 pages, 350 pages, with a standard deviation of 100 pages. What is the z-score associated with 80 pages? Well, an 80-page book, you say. Well, the z-score is going to be 80 minus the mean of 350 divided by a standard deviation of 100. Okay, so we have that, which of course is negative 2.7. Alright, so that is the z-score. Okay, so that means that an 80-page book is almost 3 standard deviations below the mean. That's really low. Alright, so what is the probability that a randomly selected book will be 80 pages or less? Well, to turn this z-score into a probability or percentage, we need to look at a table of z-score values. Okay, so this is called the standard normal cumulative probability table. But this is a table of percentages. So the way this works is if you give me a z-score, alright, this picture helps. If you give me a z-score, this chart somehow tells you what percentage of the data is less than that particular z-score. And here's how it works. The table gives the probability to the left of any z-score. So for example, say if you had a z-score of 1.23. These first two numbers, the 1.2, tell you which row to look at, and the 3 tells you which column at which to look. Okay, so the last number is the column. So let's see what in the world am I talking about. Okay, so first we look for the 1.2. These are all negative, so I keep going. Positives over here. So here you see I've got the 1.2 right there. That is not a highlighter. Okay, thought that was going to be a highlighter. Okay, it sort of worked a little bit. So there's my 1.2. And then the 3 is right here, alright? Because it's like 1.2 and then the 3 tells me which column to look at. So that's going to be right here. Alright, so that's where I get the number 0.8907. Alright, this is the decimal form, but as a percent, this would be 89.07%. Okay, so for this z-score leads me to this table value, which tells me that the percentage of the data that's less than 1.23 is 0.8907. In other words, the percentage of data to the left of the z-score 1.23 is 89.07%. By the way, if we want the percent of data to the right, we can either take this decimal and subtract it from 1, or I could take the 89.07% and subtract from 100. But let's get back to the actual homework problem. Here we got a z-score of negative 2.7. There is no third number, so we can just use the very first column. So let's find negative 2.7 on the table of values. Well, here's negative 2.7 right here. And since it's not 2.71 or 2.72, it's just negative 2.7 and that's it, then that means we're in the 0 column. So the decimal is 0.0035. So therefore the probability of randomly picking a book with less than 80 pages is 0.0035, which is 0.35%. So it's considerably less than 0.5%. Okay, number 3. The results of a test are normally distributed with an average of 63 and a standard deviation of 7. You made an 80. What is the z-score associated with this grade? Well, the z-score is going to be your score minus the mean divided by the standard deviation. Alright, so we have 80 minus 63 over, what was it, 6? I forgot. Oh, it was 7. That's why I look, people. Alright, so that is 2.43. Got to round up. So that's the z-score. Your teacher decides to curve the grades by changing the mean to a 70 and the standard deviation to a 4 while keeping your z-score the same. What would your new grade be? This sounds like an interesting way to curve. I might have to try this instead of the square root curve next time you guys horribly fail something. It's like next week, I guess. This 2.43, we're keeping the z-score the same, so that means we're going to keep the 2.43. You're going to have a new score, so we're just going to call that x because we don't know what it will be. The mean is changing to a 70 and a new standard deviation of 4. So if we solve this, we should get your new curved grade. So of course we will multiply both sides by 4. Okay, so 4 times 2.43. Alright, so we got that 9.72. Is equal to x minus 70. And then we will add 70 to both sides. So that's going to give us 79.72. Alright, so this is your new curved grade. So your old grade was an 80, and your curved grade is a 79.72. So your grade goes down with this curve, so I'm loving this curve. Much better than the square root curve. Alright, number 4. Okay, let's see how we can use z-scores to compare the SAT and the ACT again. Among all of a particular college's applicants who take the SAT, the mean score is 1,500 with a standard deviation of 240. Among all of the applicants who take the ACT, the mean score is 21 with a standard deviation of 6. Bobby scored 1,740 on the SAT. Kathy scored 30 on the ACT. Okay. Among the SAT scores at this college, what proportion of applicants scored higher than Bobby? So, we need to turn Bobby's score into a z-score and find it on the table of values. So let's do that. So we'll do Bobby here in blue. So Bobby's z-score, let's see, where's Bobby here? Bobby scored 1,740 on the SAT. So we do his value minus the mean, which is 1,500, divided by the standard deviation of 240. Okay, that's going to give us Bobby's z-score. Alright, so as you can see, Bobby's z-score is turning out to be 1. So he's 1 standard deviation above the mean. So let's write that down. Okay, so what proportion of applicants scored higher than Bobby? Well, let's look at the table for z-score of 1.0. Okay, so here we have negative z-scores. So let's just keep looking. There's 0. Okay, alright, so here's 1.0 right here. So, whoops, that's too many. So this is the value that we have to look at. But remember, this table is telling us the percentage of data that is less than a particular z-score. So we have to be careful because this question is asking what proportion of applicants scored higher than Bobby, not less. So this number tells us that 84.13% of the data is less than Bobby. So if we want to know the percent that scored higher than Bobby, we can just subtract this from 100. So if we do 100 minus 84.13, we get 15.87. So 15.87% scored higher. Now, among the ACT scores at this college, what proportion of applicants scored higher than Kathy? Well, let's do a Kathy z-score, shall we? We'll do Kathy in pink, not to be sexist with the colors, but just because that's the way it's going down. Z-score. What did Kathy do? Alright, Kathy scored a 30. The mean on her ACT is 21 with a standard deviation of 6. So 30 minus 21 over 6. Okay, so that z-score is 1.5. So you can see she did a little bit better than Bobby. Alright, because she scored 1.5 standard deviations above the mean instead of just 1 standard deviation above the mean. Anyway, what proportion of applicants scored higher than Kathy? Well, let's turn 1.5 z-score into a percentage. Let's find it on the table of values. Okay, so here's 1.5. So that means we need to look at this number right here. Now remember, this number reflects the percentage of applicants who scored below Kathy. Did I say Kathy? Yeah. So we have to be careful. If we want the percentage of applicants that score higher than Kathy, then we need to take this number and subtract it from 100. Okay, so what we have here is 93.32. All right, 93.32% scores below. So let's see, 93.32% scored below Kathy. So we'll just subtract this from 100. So we'll do 100 minus 93.32. Is that what I said? Yeah. So that means 6.68% scored above. Okay, so remember, the table of values always gives you percents that are below the z-score. If you want above, you have to subtract from 100. So part C, who did better on their standardized test, Bobby or Kathy? Well, I think it's clear that Kathy scored better. Only 6.68% of the applicants scored better than Kathy, whereas 15.87% scored better than Bobby. So Kathy did better. So you could write it up that way. Kathy did better than Bobby since her score is 1.5 standard deviations above the mean, 93rd percentile, while Bobby's score is only 1 standard deviation above the mean, 84th percentile. Now there's that word percentile. This number is coming right off of that table. It's the first number we saw when we looked up Bobby's z-score of 1, and we saw that 84% of the people scored less than Bobby. So another way of saying that is that Bobby's score is at the 84th percentile. So same thing with Kathy. When we looked up her z-score of 1.5, and we saw 93.32% of the people scored below Kathy. All right, about 93% of the people scored below Kathy. Again, another way of saying that is that Kathy's score is at the 93rd percentile. Okay, number 5. The temperature is recorded at 60 airports in a region. The average temperature is 67 degrees with a standard deviation of 5 degrees. What is the z-score for a temperature of 68 degrees? We will calculate the z-score this way. We'll take that 68 degrees, subtract the mean, divide by the standard deviation. So that's going to give us a z-score of 1/5, which is equal to 0.2. What is the probability that the temperature at a randomly selected airport is no more than 68 degrees? Okay, so that means 68 degrees or less. So we'll be able to read this number right off the table of values. So let's find 0.2 on the z-score chart. Well, there it is right there. 0.2 is right here. So that means we are dealing with this number. That's 57.93% of the airports should be less than this number. 57.93. Almost 58% of the airports are cooler. How many of the 60 airports had a temperature recorded below 60 degrees? Well, let's take 57.93% of 60. If you want to take 57.93%, you just multiply 0.5793 times 60. Alright, this is how you take 57.93%. So I'm getting 34.8, so about 35, approximately 35. Okay, one more question. Unusual heights. Assume that adult males have heights with a mean of 69 inches and a standard deviation of 2.8 inches. The actor Danny DeVito is 5 feet tall. The NBA basketball player and sometimes actor Shaquille O'Neal is 7 feet 1 inch tall. Who has a more unusual height? Well, let's convert both of these heights into z-scores. Alright, so let's find a z-score for Danny DeVito at 5 feet tall. Well, I almost tried to put 5 feet into the z-score formula, but I immediately ran into trouble because the other numbers are in inches. The mean is in inches and the standard deviation is in inches. So I can't use feet. Alright, 5 feet, that's 5 times 12. That is 60 inches. So when I do Danny, I'm going to talk about the fact that he is 60 inches tall. So 60 inches minus the mean of 69 inches divided by the standard deviation of 2.8. This will give us the z-score for Danny. Negative 3.21. So Danny's height is negative 3.21 standard deviations. Well, let me say it differently. Danny's height is 3.21 standard deviations below the mean. Alright, that's very, very low. Now, let's look at Shaquille. We'll call him Shaq because we're such good friends. So his z-score is going to come from 7 feet 1 inches. 7 times 12 is 84. 1 more inch is 85. So Shaq is 85 inches tall. Minus the mean of 69 divided by 2.8. That's going to give us Shaq's z-score. 5.71. So Shaq's height is 5.71 standard deviations above the mean. So Shaq is much further above the mean than Danny is below the mean. So Shaq has a much more unusual height. He's much more unusually tall than Danny is unusually short. They'd be the same amount of unusual if let's say one of them was -3 and one of them was +3. That would be the same amount of unusual. But Shaq is further away from the mean. So I can write it up this way. Shaq's height is more unusual since it is 5.7 standard deviations above the mean, whereas Danny's height is only 3.2 standard deviations below the mean. Here endeth the lesson.